of the first 3 worksheets and completed all that, and also some of the questions from the module which I had suggested you to do. So with these techniques and discussion of methods, etc., you should be in a position to be able to differentiate any and every function given to you, at least at the physics level. Okay. So moving ahead, today we will start understanding more and more types of applications of differentiation and how to apply the various techniques and methods like chain rule, etc., in solving physics related problems. So let's get underway. Okay, so it's quite a wide and interesting subject, the various types of applications of differential calculus. But first up, we will see the type of application. Actually, we discussed a couple of examples in the last lecture also from exercise 3 about that how we use differentiation as a rate measure. Okay, so differentiation used to measure rate of change. So from this point onwards, when we refer to the term rate of change, we generally mean that we're talking about instantaneous rate of change. Okay, so there are, for example, there are direct applications. Like in kinematics, okay, for motion along a straight line, let's say along the x-axis, okay, if position x is known as a function of time, then velocity is defined as the instantaneous rate of position with respect to time, rate of change of position with respect to time. So it becomes derivative of this. So derivative of f as a function of t. Okay. So here, when we mean the term velocity, immediately we are talking about instantaneous velocity. The default meaning of the term velocity is instantaneous, not average. Just like the default meaning of the term rate of change is instantaneous rate of change and not average. So that is equal to the instantaneous rate of change of displacement with respect to time. Okay. And speed. Again, by speed we mean instantaneous speed, not average. It becomes just modulus of this velocity. So in case of one-dimensional motion, the velocity can either be positive or negative, because the direction can either be along the positive x-axis or negative x-axis, and we can define the speed as just the magnitude of that velocity. Also, acceleration, that becomes instantaneous rate of change of velocity with respect to time. So this is an example of the direct application of differentiation as a rate measure or as a measure of the rate of change. Okay. Or another example could be Newton's second law. net force acting on a body is equal to the instantaneous rate of change of momentum. With respect to time. So this is the instantaneous value of net force. That is equal to the instantaneous rate of change of momentum p with respect to time t. Okay, so let's just make a quick note of this if you want to. Then we'll look at an example or two based on this. Okay. So let's say we have this situation. A particle moves along the x-axis such that its position x in meters as a function of time in seconds is given by the relation x is equal to this 3t square minus 2t cube. So this is position as a function of time. So we want to find its instantaneous velocity. Actually, we can just use the term velocity. From now on, when we use the term velocity or when we use the term rate of change, the default meaning of it is that we're talking about instantaneous velocity or instantaneous rate of change. We want to find the velocity v, okay, and speed, that is instantaneous speed, that is modulus of velocity, as functions of time. So from that, now we want to find the instantaneous velocity and the speed, that is mod of v, at the particular instance t equal to 0, t equal to 0.5 seconds, t equal to 1 second, and t equal to 1.5 seconds. And then we want to find the magnitude of acceleration, or let's say we want to find the acceleration and its magnitude, both the things. At the same 4 instance. Okay, so just start working this question out. Okay, so you'll see that the type of expression given to us, x is equal to 3t square minus 2t cube, is not familiar for us from our earlier knowledge of kinematics, because we were limited to situations where the acceleration was uniform. So the position or displacement, whatever you think of it, should be a quadratic function of time, like ut plus half at square. But that only happens when the acceleration is uniform. So obviously here, if we are getting the position or displacement x as a cubic function of time, That means we are dealing with a situation of non-uniform acceleration. And that you will see the moment we come to this. When we come to the third part, you'll see that it has a different acceleration at these various instants of time. So this is an example of a motion where the acceleration is variable. So particularly in something like this, you will see that calculus becomes compulsory for us to solve the entire situation. We don't have a direct formula that, we can compare the given equation with the standard formula ut plus half at square, and from that we can find the velocity as u plus at. We can't do that over here because it's not part of that standard system where acceleration is uniform. It's a different type of case where we have a non-uniform acceleration. So we have to rely on our understanding of calculus to solve this kind of a situation. Okay. Having said that, of course, here it's a direct application because we directly know that velocity is rate of change of displacement and acceleration is rate of change of velocity. So we just have to use the differentiation operator directly. Okay. So try this out and start sending me the answers. Very good, Kirti, that's correct. First part is correct for you. Now you have to also just think that what is the difference between velocity and speed? Okay, because both the things have been asked separately. Yes, Anirudh, correct. That's very good. Yes, Anirudh, that's correct. Very good. So you can see that we will start with the first part by just applying the definition of instantaneous velocity. It is instantaneous rate of change of position or displacement with respect to time. So now that we have done so much of differentiation practice, this comes naturally to us. Okay, so we can even factorize it and write it. Okay. So both of them are fine. We can write it this way also. There's no problem. So whether we leave the answer this way or this way, it makes no difference. Both are correct. But when we talk about speed, you have to be mindful of the fact that it is modulus of velocity. So it is magnitude of 60 minus 60 square. So this shows us that, for example, at a time greater than 1 second, the velocity will become negative, but the speed will be modulus of that negative quantity. So that is the difference between the formula for speed, which will be modulus of 60 minus 60 square, and the formula for velocity, which will simply be 60 minus 60 square. So hope this point is clear to all of you. So now we can start substituting the values directly. So we can see that at t equal to 0 seconds, by formula, the velocity is 0. That means speed is also 0, starting from rest. But at t equal to, for example, half a second, you'll get velocity as plus 3. Oh, sorry, plus 0.5 minus 0.25. So that's 0.25, right? So 0.25 into 6 is 1.5. So plus 1.5, which means that speed we'll take without any algebraic sign, simply 1.5 meters per second. Yes, Bhavika, how speed is different from velocity is that speed is the magnitude of velocity. So for example, you can see that when I substitute t as 0.5 seconds, I'll get velocity as a positive quantity. So speed should be just magnitude of that. Whereas, for example, at 1.5 seconds, when I check later, I will get velocity as a negative quantity, which means that speed should be just modulus of that negative quantity. So that's the difference between speed and velocity. As far as motion along a straight line is concerned, velocity has algebraic sign plus or minus depending on the direction. Speed does not have direction, it's just a magnitude. So that becomes the important difference between speed and velocity. So interestingly, you can also see that at the instant t equal to 1 second, the velocity is again becoming 0. So the speed is also magnitude of that velocity is 0. And this next part will explain why that is happening, because at a time greater than 1 second, we can see that the velocity is becoming negative. In this case, it will be minus of 6 into 1.5 into minus 0.5. No? So that is, 6 into 1.5 is 9 into minus half. So minus 4.5 meters per second, which means that the speed at this instant is 4.5 meters per second. So what this part actually means, it means that the magnitude of velocity or speed equals to 4.5 meters per second, but at the direction is along the negative x-axis. Okay. So visually you can understand it like this now, that at t equal to 0, the object is starting from rest, but by the time it comes to some instant of time less than 1 second, like that 0.5 seconds that we're taken, its velocity is in the positive direction, it continues in this direction. But the instant t equal to 1 second, it's momentarily at rest again. Okay. So this is momentarily at rest at t equal to 1 seconds. Okay. And thereafter it turns back. So that's why now at some t greater than 1 second, it's having negative velocity at any time greater than 1 second. So it's making this kind of trip. It's starting from here, turning back, and then coming like this. So this turning is happening at t equal to 1 second. Okay, now come to the acceleration, the third part. Okay, try to work it out. So you've got the velocity as a function of time. Above you can see v is 60 minus 60 square. So differentiate that once more and you'll get the acceleration as a function of time. Okay, very good. That's correct. Anirudh, just check your formula of differentiation. Kirti and yeah, now it's correct. Second time you worked it out is correct. Anirudh.
Yes, so first I divided 3t square minus 3t cube by t and did it.
Understood the difference, right? It's coming from differentiation actually, right?
Yes, sir.
So instantaneous acceleration is defined as rate of change of instantaneous velocity. So that's differentiation of the velocity that we got earlier. That was here. This formula 60 minus 60 square. This is the acceleration as a function of time. Okay. Now you can observe one thing about this function. In fact, two things you can see, that acceleration is variable. It is not a uniform acceleration, or you can say it is non-uniform. Okay. And second, you can see that the acceleration is positive for t equal to 0 to 0.5 seconds. Okay. But the acceleration becomes negative for t greater than 0.5 seconds. In fact, that's why the particle starts from rest, picks up speed, but then eventually stops momentarily at 1 second. And then it comes back. So it has a negative direction of velocity. So that is evident in the above diagram we had made about how the motion actually looks like on the x-axis. So anyhow, so now let's see. So the value of A and the magnitude of acceleration at t equal to 0 plus 6 meters per second square. So it has a magnitude of 6 meters per second square along the positive x-axis. At t equal to 0.5 seconds, acceleration is 0. At t equal to 1 second, the acceleration has become minus 6 meters per second square. So that means the magnitude of acceleration is 6, but the direction is negative x-axis. So the minus 9, is it? No. Minus 12, isn't it? Okay, so hope this application is clear to all of you. Now next, let's move on to another type of application of differentiation. Okay, so application of chain rule to measure rate of change. So this occurs when we have something like this in general, that suppose if x is a function of time, where x is any physical quantity. Okay, and this is a function of time. Okay. And we have another physical quantity which is a function of x. So y is another physical quantity, that means another quantity which is measurable, which depends on x. Okay. Then dy by dt, that is instantaneous rate of change, of y with respect to x, sorry, y with respect to time, that can be written as instantaneous rate of change of y with respect to x into dx by dt. Okay, so that will become g prime of ft multiplied by f prime t. Okay. So this is the chain rule concept here. So because x is a function of time and y is a function of x, so therefore the rate of change of y with respect to time is related to the rate of change of y with respect to x multiplied by the rate of change of x with respect to time. So we'll see this with examples, but this is the general concept over here. So application of chain rule when we are using differentiation to measure rate of change.
Wanted to, couldn't. Right in the article.
Okay, so let us look at the application of this.
This is
No, so just to explain this point, Kirti, to explain this point, what is happening is x itself is dependent on time. and y is dependent on x. So that means ultimately y is dependent on what? On time. X is a variable that depends on time and y is a variable that depends on x. So ultimately you can see that y is a composite function of x. It is it is g of ft. Okay, so that is why we are talking about the rate of change of y with respect to time, ultimately. So time is the one which is the independent variable here. So t is the independent variable. And x is also dependent on t. And via x, y is also dependent on t.
Okay, sir.
Okay, so hope the point is clear, Kirti.
Yes, sir.
Okay. So we had seen an example or two of this type of application also earlier, but let's take a fresh one today. So we have this kind of situation now. Suppose we have a solid metallic sphere and we are heating it very slowly. So accordingly, the dimensions of this sphere are increasing. So all the physical or the geometrical dimensions like radius, diameter, surface area, all these are changing with time. So this is a solid metallic sphere of radius, or start with. Now the solid metallic sphere which is being heated such that its radius r increases slowly at a uniform rate of 0.2 millimeters per second, 1/5 of a centimeter per second, or 0.5, 0.2 millimeters per second. Sorry, that is 1/5 of a millimeter per second, or 1/50th of a centimeter per second. So it's increasing at that kind of rate, very slow rate. Okay. Its mass m is equal to 5 kg. So of course the mass does not change as it expands, because we are not adding or subtracting any actual material. It's just that because of heating, the thermal energy supplied, the intermolecular distance starts increasing within the material. So the size of the material, the volume, the radius, all these things start increasing, whereas the mass remains constant. So we have to find the instantaneous rate of change of its diameter instantaneous rate of change of its surface area, instantaneous rate of change of its volume, and the instantaneous rate of change of its density. So these four things we have to relate. But at an instant when its radius is equal to 10 centimeters. So at a particular moment when the radius is equal to 10 centimeters, we have to find the value of rate of change of each of these quantities. Okay. So now this is how we have to relate this to what we just discussed, that each of these quantities, whether we are talking about diameter, surface area, or volume, or density, they are all functions of radius. And radius is changing with respect to time. So from that, using the chain rule concept, we can find the rate at which each of these quantities, like surface area, volume, or diameter, they are changing with respect to time. Okay. So just note down the data and try out this question. We'll discuss. Okay, very good, Anirudh. That's correct. So in the value of dA by dt, you have to substitute the instantaneous value of r also at that given instant. So that is equal to how much? 10 centimeters. So you will get your answer accordingly. How you substitute in units, you will either get it in centimeter square per second or millimeter square per second. Yes, Kirti, very good. That's correct. Bhavika, you will get the answer in terms of pi. So I don't know if you substituted pi as 3.14 and you're getting some approximate answer. Because the formula for surface area is 4 pi r square. So there'll be a factor of pi. Yes, Anirudh, that's correct. Okay, very good. So let's confirm all the answers. So the first part is very simple. If we talk about the diameter, say D, the diameter is twice of the radius. Okay. So therefore, the rate of change of diameter with respect to time should be 2 times the rate of change of the radius with respect to time. Now, this information is telling me that the radius is changing uniformly with time at this or 0.02 centimeters per second, whatever. So this is a uniform rate. So this will also have a uniform rate of 0.4 millimeters per second or 0.04 centimeters per second. But now when it comes to surface area, let's we denote it with S. So that is 4 pi r square. Okay. So the rate of change of surface area with respect to time will be the rate of change of 4 pi r square. Now this is where we use the chain rule. Into dr by dt. Okay, so this step to this step, this is the chain rule. Or you can basically say that rate of change of surface area with respect to time is derivative of surface area with respect to r into dr by dt. So this is 8 pi r into dr by dt. So this is the general formula. So you can understand that this is a non-uniform rate because r is changing with time. It's a non-uniform rate. Okay. So at the instant when the radius is 10 centimeters, the rate of change is 0.02 centimeters per second. This becomes this. Okay, this is at the instant when the radius is equal to 10 centimeters. So as you can see, that becomes 0.2 into 8 or 1.65 centimeters square per second. So the surface area is expanding at the rate of this much at the instant when the radius happens to be 10 centimeters. So this is at this instant. Okay, so likewise now we will relate volume also, the third part, and the fourth part density. So we'll use this formula for volume. Okay. And for density, let's say we use the symbol rho because we already used D. So density is mass per unit volume, or we can also write it as this. Okay. So we can express density as a function of volume and use chain rule, or we can express density further as a function of radius and again use chain rule. Okay, Rohan, I'll explain this again. How the 8 pi r square came. It's coming from differentiation.
Yes, sir. Yes, I got
See,
it.
in this step, got it now? Okay.
Yes, yes.
This thing, when you 8 pi is a constant, and I mean 4 pi is a constant, and r square is differentiation. Okay, very good. That's correct, Bhavika. Okay, so it's very much like the previous step, but now we are differentiating 4 by 3 pi r cube. So this is 4 by 3 pi into 3 r square into dr by dt. So that becomes 4 pi r square dr by dt. So this is a general formula we get for the instantaneous rate of change of volume. And this also shows you that it's a non-uniform rate. The volume is changing, or in this case, increasing at a non-uniform rate. So that volume rate will become 4 pi into 10 centimeters square into 0.02 centimeters per second at the instant when r is equal to 10 centimeters. So that becomes now how much? 100 into 0.02, so that's 2. So it becomes 8 pi cubic centimeters per second, or more precisely 8 into 3.14 cubic centimeters per second, or if you want to convert it to millimeters cube per second, this will become 8 pi into 10 raised by 3, or 8000 pi millimeter cube per second. So I'll just keep the answer this way: 8 pi cubic centimeters per second. But this is specifically at the instant when r is equal to 10 centimeters. Otherwise, in general, it is given by this formula. Okay. Now let's come to rate of change of. Actually, let's keep this for a minute so you can go through this. Let me know if there's any doubt in the steps. Okay, now let's come to density. So I'm using the symbol rho for density. That is a standard symbol that we use in various chapters in 11th physics. So that's why I'm using that. So density is equal to mass per unit volume. So further I can write that as, okay, or I can write it as 3m upon 4 pi r cube. Now keep in mind here that m is a constant. It is r which is the variable, such that we know that in fact dr by dt is 0.02 centimeters per second. So now I want to find rate of change of density with respect to time. So that is rate of change of density with respect to r into dr by dt. If I use this formula here, so it is differentiation of 3m by 4 pi r cube into rate of change of r. So just take the 3a by 4 pi outside because m is a constant, and differentiate 1 by r cube, and then multiply that with dr by dt. So differentiation of 1 by r cube will be how much? Minus 3 by r to the power 4. Differentiation of this kind of term using this formula. So this is the method I've applied over here. So into dr by dt. So this is a general formula for rate of change of density with respect to time. It is minus of 9m by 4 pi r to the power 4 dr by dt. So at the instant when r is, okay, again 10 centimeters, mass is of course a constant of 5 kg, and dr by dt is 0.02 centimeters per second. We can find the rate of change of density in gram per cc per second. That will be like a CGS unit, okay, or kg per meter cube per second. That will be like an SI unit. So here we can just calculate it in gram per centimeter cube per second. So we just have to convert the mass in kgs to grams.
So we can also leave the answer in kilogram per centimeter cube, right?
Yeah, but then that's like a hybrid unit system, you know?
Yes.
So it's generally preferable that either you use CGS or SI. So in SI unit system, it should be kg per meter cube per second, and CGS it should be gram per cubic centimeter per second.
So depending upon the options, you can convert it accordingly.
Yes, depending on the options, of course, you can convert, right?
Yes.
So there's nothing wrong if you write in kg per centimeter cube also, but generally the options will be either CGS or SI. Right?
Yes.
So now let's substitute the value. So at the instant when r is equal to 10 centimeters, we can see that the rate of change of density is minus 9 into, now I'm going to write this in grams. I will get this as 45 by 2 pi, right, into 10 raised power 3 into minus 2. That's 1 minus 4. So minus 3 grams per cubic centimeter per second. This is the unit that I'm getting. And the minus sign is just showing me that the density is decreasing. Now there's also another way we can verify this. We can also verify it like this, that density is equal to mass per unit volume. So here volume is changing with time. Okay. So that had the expression. So we had seen that volume was changing at the rate of, what was it? It was 8 pi cubic centimeters per second at the instant when r was 10 centimeters. So this was equal to 8 pi cubic centimeter per second at the instant when R was equal to 10 centimeters, or volume this much in cc. Okay, so now if I use this relation, I can write it as rate of change with respect to volume into dv by dt. We'll do this also. So differentiation with respect to volume of m by v. So that will become minus m by v square, because m is a constant, into dv by dt. So let's check out how much that gives us. So minus of 5000 grams divided by volume squared. So that will be 16 pi square by 9 into 10 raised power 6. Okay. Now the unit of this is grams. This is centimeter to the power 6, because cc I squared, okay, into dv by dt. Now dv by dt at that instant is 8 pi into centimeter cube per second. So this should give us the same thing. In the same unit also. You see, this is the same as this. So this is an alternate way of approaching the problem. Okay.
So from the answer we get in kilogram per centimeter cube, from there we can directly convert it, right? From the answer.
Yes, we can do that also. Just multiply it by 1000, so it will come in gram per centimeter cube per second, right?
Yes. Sir.
Yes. Any doubt, beta? Okay, so this was an example of the application of chain rule. Now let's also look at an example where we have a situation where chain rule with the application of differentiation of trigonometric functions comes into play. So a typical example of something like that is when you're looking at the angle of elevation of a vertically moving point. Okay, so for example, this is, let's say, a horizontal surface on which we have like a point from this where we are observing. So this is a stationary observer. Now this stationary observer is, let's say, looking at a particle or an object P, which is basically coming down along this line. So at the given instant, it has a downward velocity of v, and also this distance is, let us say, y. So y is changing with time, as you can see, whereas this is a stationary observer. So this distance is fixed with respect to time, and that is capital D. So now, as you know, that when this person looks up to observe that particle or object, his line of sight, suppose that is like this. So with respect to the line of sight, if the angle of the line of sight is at theta with respect to the horizontal, then we call theta as the angle of elevation. Okay, so that is the term that is given to this. So that particle or that point P has an instantaneous angle of elevation theta with respect to this observer. Okay. So theta here is the angle of elevation of the particle or point, whatever, P with respect to the observer that is shown. Okay. Now, if the particle P is falling vertically at V, okay, then find the rate of change of the angle of elevation, that is, find d theta by dt at an instant when y's value is 15 meters and v is equal to 1.2 meters per second. Capital D is given to us as 20 meters. It's a fixed quantity. So we have to find this, and we have to also find the rate of change of the distance, let's say S, between the particle P and the observer. That is, we have to find ds by dt again at an instant when y is equal to 15 meters and v is equal to 1.2 meters per second. Okay. So before we start the problem, can you first of all tell me whether the rate of change of theta, that is d theta by dt, will be a negative quantity or a positive quantity? Should theta be increasing with time or decreasing with time?
Decreasing.
Decreasing.
Sorry, a little bit louder, please.
Decreasing.
Yes, you said decreasing.
Yes, sir, decreasing.
Yeah, it's decreasing with time. You can see that. Okay. So as the particle is coming down now, you can see that for this kind of a right angle triangle, the perpendicular, the y is decreasing, whereas the base remains constant. So obviously the angle over here, theta, is decreasing. So what we expect is that d theta by dt should come out to be a negative quantity. Similarly, you can see as the particle is coming closer to ground, its distance with respect to the observer is also decreasing. So if this distance is s, then s is also a quantity which is decreasing. So ds by dt also we expect should be a negative quantity. So that's one thing you have to keep in mind. Second thing you have to keep in mind is that what is the relationship between y and v? Okay, because y is changing with time, whereas capital D is constant. So how do we find the relation between these two things? What is dy by dt? Yes, anybody? What is the rate of change of y? It is equal to v only, no? But very importantly, it is v with a negative sign. Okay, because again you can see that the direction of v is such that the quantity y, that is the vertical height of that point p, is decreasing. So rate of change of y, dy by dt, should be what? It should be equal to minus v. Okay, so these are the things that we have to keep in mind, that y is changing with time such that at the given instant dy by dt is the instantaneous value of v. Okay.
So y is equal to vt.
That's only if v is constant, na? And that too it will be some initial value minus vt, na? But that information we don't have, na? In all probability that's not the case, because it's free fall, na? So unless it's like a featherweight kind of object which is falling such that the air resistance acting on it balances the weight. So unless it's some kind of special case like that, most probably definitely even with air resistance present, it should have some acceleration. Or if it's like a high density object like a stone or a metallic piece or something like that, then its acceleration will be almost equal to g. The air resistance will be negligible. Okay, so that we don't know over here that v is constant or not, but we are not concerned with that also, no? Because we want to find out just at that instant the rate of change of theta. So what we have to do is we have to relate theta with y, and then use the fact that d theta by dt will be related to dy by dt, and dy by dt in this case will be how much? It will be minus of v. So at the moment that we are talking about, the value of y is 15, but the rate of change of y is how much? It is minus 1.2 meters per second. Okay, so hope you are clear about this. Now, how we'll relate theta with y? We'll relate it by trigonometry. Okay, so use the trigonometry of the triangle to find the relationship between theta and y, and then use chain rule to find the relationship between d theta by dt and dy by dt, where dy by dt is clearly how much? It is minus of v. So just try this out, we'll discuss soon. Okay, so just received answers from only a couple of people yet, so I'm just going forward with a little bit more about this. So if you look at the particular triangle at the given instant of time, you realize that it's a 3, 4, 5 triangle, because at that moment when we are calculating the exact value of this angle of elevation and its rate of change, we can see that the instantaneous value of y is 15 meters. This is instantaneous. Whereas this distance 20 meters, this is a fixed distance. Okay. And this v at this moment is 1.2 meters per second. Now this may be instantaneous, this may be fixed, we don't know. Okay, but the important thing is that the rate of change is this much. Okay. And therefore this value of s at that particular instant, you will see, will come out to be 25 meters. Okay, by using, so this is an instantaneous value. So you'll also realize that theta at this particular instant is 37 degrees, because it's tan inverse of 3/4. Okay. Now the first part, we want to find d theta by dt at this particular instant. So we can see that dy by dt is minus of v, because y is decreasing at the rate of this. Okay, so we'll relate these two now. So we can see that tan theta is equal to y by d. So this is the relation between theta and y. So from this, how will we generate this? So we'll just differentiate on both sides. So rate of change of tan theta with respect to time should be equal to rate of change of y by d with respect to time. So for this side, we'll have to use chain rule. So differentiation of tan theta into d theta by dt. On that side, we can just take 1 by d common, because it's a constant. Okay, so this is your chain rule step again. From here to here, this is your chain rule. Now what is differentiation of tan theta? Anybody can tell me, you remember the value of differentiation of tan theta?
Sec square theta.
Yes, very good. So sec square theta into the instantaneous rate of change d theta by dt should be equal to 1 by d into dy by dt. So the general relationship between these two quantities, the rate of change of theta or the angle of elevation, how it is changing with respect to time, and how y is changing with respect to time, the relationship is, when you take sec square theta on that side, 1 by sec square becomes cos square. So cos square theta by d into dy by dt. Okay. Now if I substitute everything in SI unit here, I should get d theta by dt in SI unit, which is radians per second. So I'll get d theta by dt as, so at this particular instant, now this is the general formula. Now we want to calculate it at the instant when y is 15 meters, so theta is 37 degrees, and dy by dt or v is given to us as 1.2 meters per second. So dy by dt, remember, will be minus of v. So we'll substitute this also here. So it is cos square 37 degrees, okay, divided by 20 meters, okay, into minus 1.2 meters per second. Okay. So meter will cancel. Cos square 37 is a dimensionless factor, unitless factor. So the rate of change of angle that we'll get will be in per second, or more precisely radians per second. So it will become minus of 0.64 into 1.2 divided by 20. Now you can say the unit is actually per second, but when we express it in per second, it's actually radian per second. Because what is 1 radian? It is 1 meter divided by 1 meter. Now, any angle expressed in radians is the ratio of arc length to radius. It is S by R. Okay. So basically 1 radian is equal to just the number 1. It's unitless. But that is, of course, in degrees, 1 radian is equivalent to pi by 180. Oh, sorry, 180 by pi. So anyhow, so coming back to this is the value of d theta by dt, and it's a negative quantity, as you can see, as expected, because theta is decreasing with time, so it should be a negative quantity. So this is the first part, rate of change of theta with respect to time. Now similarly, we'll find out the second part, the rate of change of s with respect to time, by relating s with y and then using chain rule, or we can even relate s with theta and use chain rule, because now we know d theta by dt also at this instant.
So how do you get theta is 37 degrees?
That is from the trigonometry of this triangle. Now you can see tan 37, for example, or tan theta is 15 by 20. So theta is tan inverse of 3 by 4, which by definition you know is 37 degrees. Na? Vectors में आपने पढ़ा होगा ना, 37, 53, all these angles.
Yes, sir.
So it's a 3, 4, 5 type of triangle. The ratio is 3x is to 4x is to 5x. So it's a, this angle is 37, this one is 53.
So what if we get a triangle other than 3, 4, 5?
What if we get a triangle for?
Other than 3, 4, 5 triangle.
Then we'll use that corresponding value. So for example, suppose here y had been 10 meters instead of 15 meters, then theta would not be one of those regular ones, but we can still calculate the value of tan theta, no? Because it is 10 by 2, I mean 10 by 20, so it's half. So from that we can find the hypotenuse. It would have become root 5. So cos theta would have become how much? 2 by root 5. Sin theta would be 1 by root 5. So basically, whatever the instantaneous value of y and whatever is the value of d given, you can calculate s by using this. And then depending on what you need, like here I need cos theta, so it is d by s. If I needed sin theta, it would be y by s, like that. So we'd use the trigonometry of that triangle.
Yes, sir.
Okay, clear, Nanidud?
Yes, sir.
Okay. Yeah, so Bhavika, I'm explaining the first part again. So what we did in the first part, see, what we wanted to do was we wanted to find out the rate of change of theta. D theta by dt is what our target is. This is what we're trying to find out. But what we know the value of dy by dt. We know it's minus v, and v's value is given to us at this instant. So to find d theta by dt, the first thing I have to do is I have to relate y with theta. So I use trigonometry. The tan theta is equal to y by d. So I've got a relation between theta and y. And then I differentiate that so that I get a relation between d theta by dt and dy by dt. So that's how I get this relation.
Okay.
So so ultimately my d theta by dt is cos square theta upon d into minus of v. So at this particular instant, theta is 37. So I replace it with that. Capital D is of course fixed of 20 meters. And at this particular instant, what is the value of v? It is 1.2 meters per second. So I've substituted these values here. Just a moment, I'll share the screen again. So on substituting those particular values, I'm getting the instantaneous value of d theta by dt as this quantity, which I think will come out to be minus of 0.038, if I'm not mistaken, radians per second. Again, I'm using the value of cos 37. Cos 37 is 4 by 5 or 0.8. That's how I substituted cos square 37 as 0.64. Okay, now next part, we want to find out ds by dt, the rate at which that distance s is changing with respect to time. So that distance s is nothing but the hypotenuse now. So again, we'll relate it. The easier way to relate it will be by Pythagoras theorem here. We can of course use theta also, but sorry, this is v. So I know that dy by dt is equal to minus v. So what I'll do is I'll relate s with y and then find ds by dt as the derivative of this function into dy by dt. Okay. So it's very simple. S is equal to square root of capital D square plus y square. So ds by dt will become differentiation of this function, okay, into dy by dt. Okay. Now notice that this function that we are talking about now, s, it is a composite function. So its differentiation we'll have to do by chain rule. So this differentiation itself you use chain rule. So on doing those steps, just try them out just now yourself. Okay. So the chain rule steps here, this should come out to be y upon root of d square plus y square. I'll show you the steps in a moment, but just try it out yourself. So on doing this, you should get this like this. That this will be so this is this term actually, and that's how it comes out to be this. So you notice that so further this quantity is nothing but sine theta into minus v. This is what our ds by dt is in general. Okay. So at this particular instant, it will be minus of 1.2 into sine 37. This will be the instantaneous rate. So there's a bit of work for you to do over here in case, this step is not directly clear how we've got this differentiation, then come from this to this step by using chain rule. So substitute d square plus y square or y square plus d square as z. So y is equal to square root of z. So then your dy by, sorry, not y, s s is equal to square root of z. So ds by dy will become ds by dz into dz by dy. So differentiation of z with respect to, this differentiation of root z is 1 by 2 root z, and differentiation of z with respect to y is 2y. So that's how we come to this step. So this step.
So,
Yes.
while differentiating that square root of d square plus y square, we won't write 2d into 2y. I mean, d square plus y square ka
No,
bhi
capital D is
differentiate.
a constant, beta. So capital D is a constant. So when we are doing this step here, na, this one
Yeah,
by dy. तो यहाँ पे z क्या है? Okay.
20.
Yeah.
अच्छा,
Y
ठीक
square
है.
plus d square, na. Now
Yeah, yeah.
capital D is a constant here, na. So its derivative is 0.
Yes, sir.
Na? So that's why we are
Understood.
just left with 2y. Got it, no?
Yes, sir.
Okay. So I hope this is clear. Any other doubt in this?
So
Okay.
can you
Yes.
explain again that that 1 upon 2 into how that square root z came means?
Okay. Let's do this whole thing again. Okay. So see, what we are trying to do is we have got s is equal to square root of d square plus y square or y square plus d square, whatever we write it as. Okay. So now from this we want to find out ds by dt. So that is ds by dy into dy by dt. Okay. So in this term we know is minus b. So that's done. But what about this term? So we have to differentiate this. Okay. So we have to find ds by dy. So now you notice s is what type of function of y? S is a composite function of y. It's this type of function. Because on y we are first operating d square plus y square. That's a quadratic function. Okay. And then we are operating the square root function. So that is square root of d square plus y square. So we have to use chain rule. So for ds by dy, we have to use chain rule. So the first step is substitution. So s is square root of d square plus y square. So substitute the quantity inside the square root as a dummy variable. Okay, this is clear now?
Yes, sir.
Okay. So what does s become? S becomes square root of z. So now differentiation of s with respect to y, this thing that we are calculating, this is equal to what? It is differentiation of s with respect to z, because I have related s with z, into differentiation of z with respect to y, because z is related in terms of y. Okay. So this is differentiation of root z with respect to z, and this is differentiation of d square plus y square with respect to y. So differentiation of square root of z will become 1 by 2 root z. This step is clear.
Yes, sir.
Z to the power half, and so it become half into z to the power half minus 1. Okay, that's how this step is coming. And differentiation of d square is 0 because d is a constant, and differentiation of y square is 2y. So we are left with y by root z, but z was the dummy variable, so we have to resubstitute. So the final step, when we resubstitute, sorry, dy, when we resubstitute this, it becomes y upon square root of d square plus y square. Okay. So this term becomes this much now.
Yes, I got it. Thank you, sir.
Okay. So it's particularly for these type of applications, the chain rule concept is very important, because as you can see, we are applying chain rule multiple times here. Once we have already used it here, this step itself is chain rule. Okay, that ds by dt is this is chain rule. And then again, while differentiating this also, we are using chain rule. So for this one's differentiation also, we are using chain rule once more. Okay, so values and everything clear in the previous question now? Okay, so
Yes,
before
sir.
before we wind up today's lecture, one last thing we will look at, okay, is the application of derivatives let's say f prime x of a function to understand the behavior of the function. So what we mean by behavior of the function is whether the function is increasing, okay, or decreasing. In nature. Okay. So just to illustrate this point, suppose I take an arbitrary graph of a function without defining the formula of the function. So I've not defined the function by any equation, but I'm just assuming that whatever the equation of the function, its graph is something like this, suppose. Okay. Where this point is, let's say it starts from the point A, and then this point somewhere here is C, let's say. Okay. In fact, let's just concentrate on this part, forget about this part for the moment. Okay. So what we can see is that the function, whatever its formula, it has such a nature that from A to B, the function is increasing because the value of y is increasing as you increase the value of x. But then after crossing the point B, x equal to B, it starts decreasing. So that is the behavior of the function. So here you can see that for this function, fx increases with x. Okay. For the interval x belonging to A to B. Okay. So this kind of interval is also written like this, that it is greater than A and less than B. Okay. Whereas the function decreases with x for x belonging to the interval B to C, or the moment x becomes greater than B, then up to the point C. Beyond C, what is happening, we can't tell because the graph is given only up to here. But in this interval from B to C, we can see that the value of the function fx is decreasing as x is increasing. So that is what we mean by saying that the function is increasing or decreasing. Now, how does this correlate with differentiation? So if you see the slope of the tangent at any point between A and B, it will be what kind of slope? It will be a positive slope. M will be positive for this kind of a tangent. Whereas if we draw the tangent at any point where the function is decreasing, the slope of the tangent will be what? Negative. So what is the slope of the tangent? It is the value of the derivative. No? So the value of the derivative tells me this thing. So therefore, this will imply that the derivative of the function will be equal to a positive quantity for x belonging to A to B. Whereas the derivative of the function will be a negative quantity for x belonging to B to C. So in other words, what we can say is that if f prime x is positive in a certain interval, okay, then that implies that the function fx increases, okay, that is increasing with respect to x in that interval. Okay, whereas if f prime x is negative in a certain interval, then it implies that the function is decreasing in that interval. Okay. So this is what we mean by the application of the derivative f prime x of a function in understanding or looking at the behavior of the function. By behavior of the function, we mean whether the function is increasing or decreasing. Okay, so as a quick example, let's see something. So we have a function like this. Suppose y is equal to x cube minus 3x. Okay. Now we don't know the graph of the function. Okay. But we can kind of understand that it's going to be a situation where, for example, if you see between for smaller values of x, like 0.5 or 0.25 or something, the 3x term dominates over the cubic term. So it's a decreasing kind of graph. Whereas the moment x becomes larger than a certain value, like for example, when it's x is 2 or 5 or something like that, the cubic term is dominating. So it's becoming an increasing function. So this function should have a dual nature. It should decrease in a certain interval of x, and again it should increase in a certain interval of x later. So if we want to find the interval of x for which y increases or decreases, okay, then we can do the simple exercise that y being x cube minus 3x, okay, the rate of change dy by dx you will get by differentiating this. So that is 3x square minus 3, or that is 3 into x square minus 1. So you will see from this that the rate of change is positive for x square minus 1 being greater than 0. So that means that is for x being greater than 1 or x being less than minus 1. Whereas the rate of change is negative for x square minus 1 being less than 0. That means for x square being less than 1. Okay. So that means for x being greater than minus 1 and less than 1. So ultimately, this is the interval where the rate of change is negative, right? And this is the interval where the rate of change is positive. So what we can tell about the function, therefore, okay, the function is such that the function fx increases for x belonging to minus infinity to minus 1, because it's less than minus 1, okay, and x belonging to 1 to infinity, because again it's positive when x is greater than 1. But on the other hand, the function is also decreasing for x belonging to the interval between minus 1 and 1. Okay. So basically the function has some kind of nature like this, that it's increasing, then decreasing, then again increasing. Okay. So it increases up to x equal to minus 1. Then it decreases from x equal to minus 1 to x equal to 1. And then after that, again, it's increasing. So this would be at least the shape of the function x cube minus 3x. Okay. So this is clear to all of you, or at least those of you who are there at the moment. Okay.
Yes, sir.
Sir,
Yes.
sir, can you explain the first part again where x is greater than 1 and x is less than minus
Sorry, Kirti, come again. The first part.
1? Where x is greater than 1 and x is less than 1.
Okay. Okay. So you understood up to this step, now the differentiation part.
Yes, sir.
Okay. Now we have to solve this. Now dy by dx is greater than 0. So that means 3 into x square minus 1 is greater than 0. So x square minus 1 is greater than 0 because 3 is a positive number. So this is clear.
Yes, sir. Clear.
Okay. Now next thing what we are saying, that x minus 1 into x plus 1 is greater than 0. Okay.
Yes, sir.
Now in maths you learned something called wavy curve method.
Yes, sir. We have.
पढ़ा है ना, तो उसमें देखो क्या होता है, ये between minus 1 and 1, if you look at the quantity x minus 1, this is negative here and positive here, right? And if you look at the quantity x plus 1, sorry, x minus 1 is negative up to 1, right? If you look at x plus 1, it's negative here and becomes positive here. So now you understood now?
Yes, sir. Yes,
So the
sir.
product of these two things, the product of these two things is positive when x is less than minus 1 because it's negative into negative. And then again, it's positive when x is greater than 1. Okay. So that's how for this interval, the product, okay, is becoming, so that's how I got this one. Okay. And again, for this interval, the product is positive. Okay. So for that, I've got greater than 1. So that's how I'm getting this thing. The union of less than minus 1 and greater than 1. Okay, Beta, this is clear?
Yes, sir. Thank you, sir.
Oh, very good. Okay, so don't worry, we'll see more questions like this in the next lecture. Okay, this is just an introduction to this part today, the last part, which is the behavior of the function, whether it is increasing or decreasing. So next time we'll also see that this kind of a point where the function reaches a peak, it is called maximum. And this type of a point where it reaches a dip, it is called minima. And we'll see how to use differentiation to calculate the values at these 2 points also. Okay. So as I said, I'll be sending you an assignment with some practice questions in the earlier things that we've learned, like chain rule and various methods of differentiation, plus some new type of questions which are based on what we've learned today, which is differentiation as a rate measurer. Okay, so you do that exercise along with some questions from the module this week, and that should get you well rehearsed in these kind of applications of differentiation. Okay, so that's it for today, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Okay,
Thank you,
people.
sir.
Thank you, sir.
Okay, bye.
Thank you, sir.